In this question, you will explore possible approaches to using historical sports results for making predictions about future sports matches. Two friends, Peter and Helen, are discussing ways of predicting the outcomes of international football matches involving Argentina. Peter suggests analyzing historical data to help make predictions. He lists the results of the most recent 240 matches in which Argentina played in chronological order, then considers blocks of 4 matches at a time. He counts how many times Argentina has won in each block. The following table shows his results for the 60 blocks of 4 matches. Question A. Determine the mean number of wins per block of 4 matches for Argentina. 2 marks. So when you just find mean of this data, it can be found as total sum divided by total number of items, or total frequency. So it can be found as 1 multiplied by 11 plus 2 multiplied by 21 plus 3 multiplied by 21 plus 4 times 7 divided by 11 plus 21 plus 21 plus 7. Or just using a calculator stat, edit L1 its data, L2 its frequency, and notice that when n of frequency is 0, you cannot take it into account, but when data is 0 but frequency is not 0, you must take it into account. And then just stat calc and just one variable statistics, L1, L2, and you can see that mean is 2.4. The next. Peter thinks that this data can be modeled by binomial distribution with n is 4, and decides to carry out a chi-squared goodness of fit test. Question B. Use Peter's data to write down an estimate for the probability P for this binomial model. 1 mark. It is given in data booklet that the expected value or mean for binomial is NP. And mean for this data is 2.4 and is equal to n is 4. It is given multiplied by the probability. So probability is 2.4 divided by 4 is 0.6. C. Use the binomial model to find the probability that Argentina wins 0 matches in a block of 4 matches. 1 mark. So let x be random variable number of matches that Argentina wins. So it is distributed binomially with parameters n is 4 and probability to win is 0.6, and we need what? That it wins 0 matches. So we need probability that x is 0, and just using a calculator, it's at the one point, so it's binomial PDF. When you need less or equal, it's binomial CDF. So distributions and binomial PDF, trials n is 4, probability 0.6, x is 0, and you get the result. Also, it can be calculated as so, since it wins 0 times, it means that it loses all 4 matches. And since there are no permutations, it means no rearrangements, or all outcomes are equal, it becomes a probability to lose is 0.4. So it's 0.4 multiplied by 0.4 by 0.4 by 4. So it's 0.4 to the power of 4. The next. Find the expected frequency for 0 wins. 2 marks. It's not given clearly, but it means for all 60 blocks. And again, for binomial expected value or mean, it's NP, and expected frequency for 0 wins in 60 blocks. So it's 60 multiplied by the probability for 0 wins in each block. and it's this value, and it is equal to 1.536. You may give as exact or as usual to be round to 3 significant figures. The next, as some expected frequencies are less than 5, Peter combines rows in his table to produce the following observed frequencies. He then uses the his binomial model to find appropriate expected frequencies correct to 1 decimal place. And question D. Peter uses this table to carry out a chi-squared goodness of fit test to test the hypothesis that the data follows a binomial distribution with n is 4 at the 5% significance level. For this test state, the null hypothesis it's that data follows a binomial distribution with n is 4. It's not required, but the alternative is that data doesn't follow a binomial distribution with n is 4. The next, the number of degrees of freedom, 1 mark, degrees of freedom, it's n-1 and -1 for each estimated parameter. And don't get confused, it's not this n, it's number of pairs here, observed and expected, 1, 2, 3, 4, so it's 4 minus 1, and since probability is estimated and it is used to calculate expected frequencies, so it's -1, so it's 2. P-value, 2 marks, and then the conclusion, justifying your answer, 2 marks. So just using a calculator, goodness of fit test, and stat, edit, and you can see L3 it's observed, L4 is expected. Then again stat, tests, and we need goodness of fit. Observed L3, expected L4, degrees of freedom it's 2, and just calculate, and we get the required p-value 0.954 to 3 significant figures. Then you remember, if p-value is less than significance level, you accept the alternative hypothesis. And here, since p-value is greater than 5%, we accept the null hypothesis, override that there is insufficient evidence to reject H0. It means that we accept the null hypothesis. The next, using Peter's binomial model, find the probability that Argentina will win at least one of the next 4 international football matches, 2 marks. So the same distribution, 4 and probability to win 0.6, and we need to win at least one. So we need x is greater or equal than 1. It can be rewritten as 1 minus probability that x is less or equal than 0, and in general why we rewrite less or equal, because it's a binomial CDF and can be calculated, but here less or equal than 0 is just 1 point x is 0, but x is 0 is already calculated, so it just 1 minus 0.0256, and it's 0.9744. You may give as usual to 3 significant figures. The next, Helen thinks that a better prediction might be made by considering the transition between matches. To keep the model simple, she decides to use only 2 states. Argentina won, it's A, or Argentina did not win. It's state B. Helen looks at Peter's list of results and counts the number of times that Argentina won twice in succession, AA. Argentina won, then did not win, AB. Argentina did not win, then won, BA. And Argentina did not win twice in succession, BB. Quite easy to understand. It means win-win, win-lose, lose-win, lose-lose. And question F. Given that Argentina won the previous match, so initial state is A, shows that Helen's estimate for the probability of Argentina winning the next match is 17/29. So we can see there that the initial state is A, and there are two possible outcomes, to win and to lose. And you can see that to win, again, it's 85 out of 145, so it becomes 85 out of 145, and we can divide by 5 to get 17/29 as required. And then write down the transition matrix T for Helen's model, 2 marks. So transition matrix becomes, and you remember that you should read it as from to, and AB, it's not necessary to write AB. So from A to A, it's our 17/29, and you remember that each column adds up to 1. It's total probability, which is 1, so this can be found as 1 minus 17/29, which is what, 12/29. And if initial state is B, from B to A, so we consider these two, and if initial state is B, you can see that there are two possible outcomes, and ratio is 62/32, so there are 94 in total, and probability that the second is A, so it's 62/94, and it's 31/47. And then it can be found as 1 minus this, and it's what? It's 16/47. You can give this matrix as decimals, but for and here to be round to 3 significant figures, but for further calculations you should take as exact just one more decimal place, or 1 or 2 decimal places to be correct if you round to 3 significant figures finally. And as decimals it looks like this. The next, G, shows that the characteristic polynomial of T is it arises when we need what eigenvalues, and actually the next questions are to find eigenvalues and eigenvectors. So how to find eigenvalues? We can see the determinant of the next 2 by 2 matrix to be 0, and on the main diagonal it becomes minus lambda minus lambda. And determinant of 2 by 2 matrix formula is given in the data booklet. It's this product minus this product, so it becomes 17/29 minus lambda multiplied by 16 over 47 minus lambda minus this product, and it should be 0, and we need expand it and simplify, and we should get this result. So let's expand it firstly. Minus 16 over 47 lambda minus 17 over 29 lambda plus lambda squared minus this product. And now let's multiply each term by 29 and by 47 to get 17 times 16 minus 16 times 29, and we can factor out minus lambda to get 17 times 47 lambda plus lambda squared multiplied by 29 and by 47, and minus 12 times 31 is 0, and 29 times 47 is this, and you can see it's correct as required. Then for lambda, it's this one. It's 16 times 29 plus 17 times 47, and it's this value as required, and then 17 times 16 minus 12 times 31 is negative 100, so we get as required. The next it's actually find the eigenvalues and corresponding eigenvectors. So we need just solve this quadratic equation, but if it's about transition matrix, one eigenvalue, it's always 1, and then I can just use sum or product rule. Sum for quadratic it's minus b over a, or product it's c over a. In general, you may use just discriminant or just using a calculator, but product is c, it's negative 100 over this value, and 1 lambda is 1, so 1 times another lambda, so the second root is just this value, or let it be the first lambda, it doesn't matter what lambda is the first, what is the second, and one solution, it's always 1 for transition. And now we need corresponding eigenvectors. To find eigenvectors, we solve the next problem. Transition matrix multiplied by some vector, which is the required eigenvector, is equal to eigenvalue multiplied by the same vector. So our matrix is over 29, 31 over 47, 12 over 29, 16 over 47, multiplied by some vector xy is equal to lambda, and let's consider for lambda 1, so it becomes negative 100 over this value xy. And then we multiply two matrices. How to multiply them? Just becomes xy, and it becomes 17 over 29x plus 31 over 47y, and when you multiply 2 by 2 matrix by 2 by 1 matrix, you get that it becomes 2 by 1 matrix and is equal to this value xy, and then we equate rows. So I write it now that it will be equal to negative 100 over this value x, and in general it's enough only one. Why? Because the second will be dependent usually. What does it mean? For example, if the first is x plus 2y is 10, the second it's like 2x is for y plus 20. It's dependent. But it may be a situation that one equation is, for example, 0 is 0, so you use the next. But here it's enough to get 1 and consider this. But let's consider the second. The second becomes 12 over 29x plus 16 over 47. Or actually, you may check that if you consider the second, you will get absolutely the same. Then we consider one equation, let it be the first, and let's simplify it, and let's move this x to the right, so it becomes negative 100 over this minus 17 over 29. And you can see that it becomes negative 31 over 47x, and you can see that it becomes just y is negative x. And for eigenvectors, it doesn't matter its length, it's important direction only, so you can take absolutely any values for x or y it to be true, and usually we take in least integers, and you can take it to be 1 for when x is 1, y is negative 1, or x maybe negative 1, y 1, it doesn't matter. So it's the first eigenvector corresponding to eigenvalue, which is what? Negative 100 over 1363. And do the same for lambda is 1. So 17 over 29, 31 over 47, 12 over 29, 16 over 47 is multiplied by xy. It's for lambda is 1. And is equal to 1 x y. Then multiply two matrices, it becomes xy, so it's 17 over 29x plus 31 over 47, y is x, and 12, definitely it's enough only the first. And if we consider, for example, the first, it becomes 31 over 47, y is 1, and 1 it's 29 over 29 minus 17 over 29, and it's what? 12 over 29x, and then we can multiply by 47 and divide by 31 to get this. and as decimal it becomes 0.627. As answer you may write to 3 significant figures, but for further calculations you should take 1 or 2 more decimal places to be as exact x, and we can take x to be 1, then y is this 0.627 to 3 significant figures. So it's P2 for lambda is 1. And the last question. In her retirement many years from now, Helen is planning to travel to 3 consecutive international football matches involving Argentina. Use Helen's model to find the probability that Argentina will win all 3 matches, 4 marks. And actually, what should you know? What is steady state vector? It's actually it's we solve a problem that the transition acts on some vector is equal to the same state, same vector. And you can see that if I write 1 here, it's absolutely the same as eigenvector corresponding to eigenvalue 1. And hence, for eigenvalue 1, this vector gives us 2 things. The first is a ratio for a long period of time. It's a ratio that Argentina wins and Argentina loses. So it wins and loses in ratio 1 to 0.627. And if we do it to be scaled to 1, how it works? It's another example. For example, if it's 10/7, if scaled to 1, it becomes there are 17 parts in total, so it's 10 over 17 and 7 over 17. Now sum is 1, its total probability it's 1, and it gives us probabilities that after a long period of time Argentina, or let's do here also be scaled to 1. So, and we need actually, I repeat that, many years from now, so we need that Argentina wins 3 matches, but the first is after a long period of time, so it can be found from steady state vector. And since our matrix is AB, so the first entry it's to win. So this vector scaled to 1, and this entry gives us what probability to win after a long period of time. And just scaled to 1, it becomes what? Just 1 divided by this 3/6 as exact. So it becomes just 1 divided by 1.62736, and it's 0.614. So probability to win the first match after a long period of time is this from steady state vector. And also steady state vector can be obtained from, if you consider this matrix to be to very large power, usually 50 is enough. So our matrix, it's transition matrix, and then just matrix A to the power of 50, for example, and you should get equal columns, and each column each it's the required steady state vector, and you can see that sum is 1, so it's in terms of probabilities, and you can see that it's the same result, 0.614, and it means that probability to win after a long period of time is this value. And then it's not after a long period of time, to win, provided the first it's to win, and it's just this from matrix. If win-win, it's this win and then win for the second, and the same for the third. It's what, 17 over 29? Squared, or as decimal, it's 0.5862, and it becomes 0.21123 significant figures. And that's all for this question.